Okay, Dmitry Mendeleev. He was a Russian chemist. He used Newland's observations and other information. So he produced the first orderly arrangement or periodic table of all known 63 elements, and he arranged them by their atomic mass, similar to what Newland's had done. However, he switched up iodine and tellurium. He lined them up according to their properties, not their atomic mass, but he couldn't really explain why. Okay, he didn't really know why he had to do that. He just knew it made sense. Okay. So here's a rough overview of what his periodic table looked like. Okay, so let me just show you. Here he has group 1, group 2. You can see this has elements that are currently in those groups. Group 3, on our modern periodic table, you notice this lines up with group 13, group 14, group 15, group 16, group 17, and then he doesn't have group 18, he has group 8. Group 8 contains a lot of the transition metals, okay? And you'll see it does not match exactly our periodic table, however, it's pretty darn accurate, so kudos to Mendeleev. So something else that is important to note about Mendeleev's table. He has gaps for not yet discovered elements. And he predicted the properties of those missing elements. In fact, he named them. Like he named an element aluminum, so close to aluminum, but not aluminum. And he predicted the properties. And you can see from this table that some of the elements that he predicted, his predicted properties were surprisingly accurate for elements that he didn't even know existed. So Mendeleev, amazing. And why did Mendeleev leave blanks in his periodic table? So he left blanks. Why did he do it? Yep, for the undiscovered elements. Now we move on to Henry Moseley. Okay, he was an English chemist, and he studied the X-ray spectra of elements. So remember we talked about the line emission spectrums. He studied those. And in that process, he realized that when elements were arranged by atomic number, remember that's the number of protons in an element, not atomic mass, the discrepancies that Mendeleev had that he couldn't explain, poof, gone. So he's like, ta-da, we have to arrange them by atomic number, not atomic mass. So how did Moseley arrange the elements in the periodic table? Yeah, by atomic number. And this is called the periodic law, which we're going to talk about. So the periodic law. When elements are arranged according to their atomic numbers, elements with similar properties appear at regular intervals. Okay, so the physical and chemical properties of elements repeat and their functions of their atomic numbers. So when we put elements in order by their atomic numbers, we will see a repetition, okay, of physical and chemical properties. So what is a group? Okay, you can see here group numbers here, 13 through 18. A group is a vertical column. Okay, so on our reference table, literally it says the word group. Don't have to memorize it. Elements in the same group share similar chemical properties. What is a period then? Well, you can see those numbers 1 through 7 here. Again, you can see also the word period on the periodic table that we use, so you don't have to memorize it. It is a horizontal row on the periodic table. Elements in the same period have the same number of occupied energy levels. So period 1, electrons only in energy level number 1. Elements in period 3 have electrons in energy level 3, energy level 2, and energy level 1. What is a vertical column on the periodic table called? Do you remember? A group. Groups are vertical. What is a horizontal row on the periodic table called? Do you remember that? A period. Periods go horizontally. And why do properties on the periodic table repeat? Do you remember? Do you remember why they repeat? Elements in the same group have the same number of valence electrons, which that is what accounts for the repetition of properties. So let's talk about main group elements. So the main group elements are the representative elements, and we consider those to be groups 1, groups 2, and then groups 13 through 18. So in terms of what we talked about before, in terms of electron configuration, that's the S block, groups 1 and 2, and the P block, groups 13 through 18. They have regular and consistent electron configuration. So that means the S block. So we're putting one electron in the S and then a second one. And then as we move across, we're putting one electron in P, then a second, then a third, then a fourth, then a fifth, then a sixth. So it's regular and consistent. And they have the same number of valence electrons. So elements in group 1, 1 valence electron. Elements in group 2, 2 valence electrons. Group 13, 3. Group 14, 4. Group 15, 5. Group 16, 6. Group 17, 7. Group 18, 8. Exception, helium. Helium only has 2, but remember, it only has 1 energy level, so that is completely full. So alkali metals, let's talk about them first. Alkali metals, group 1, okay? That's the name for group 1, alkali metals. They are obviously metals, duh, alkali metals. They are soft, okay? So you can see easily cut. They have 1 valence electron, group 1, 1 valence electron. They're very reactive. So that 1 electron, they give it up so easy. Does not take any convincing. They just give it up. Easy for them to lose that valence electron. They're the most reactive metals. Okay, so let's look. Here's where they are in the periodic table. Alkali metals. Hydrogen is not included because hydrogen is, we'll learn about it later, it's in a class by itself. It can act like a metal, it can act like a non-metal, it kind of can't decide. It's the only element that can exist without a neutron at all. So again, total oddball. So alkali metals, group 1, 1 valence electron, super reactive, okay? Very reactive. Give up that 1 electron super easy. Oh, here you go. There you go. Take it. Fine. Take it. They love to react. They will react with water to make alkaline or basic solutions, okay? There's rubidium. That's just water. Put it in water. Highly reactive. But you can see lithium, sodium, potassium, their reactivity is slightly increasing. Then you get further down the group to rubidium, and all of a sudden the activity increases because it is easier and easier to give up that electron and react. Most often they are stored in oil so that they don't react with oxygen in the air. And we never find them as pure substances, as pure elements in nature. They're going to be found in compounds. So we're not going to have sodium existing in nature because it would have reacted like this. Now, alkaline earth metals, group 2, also metals. They are harder than those in the alkali metals, and they have 2 valence electrons. So they all end with 2 in their electron configuration, so they have 2 valence electrons. They are highly reactive, so they will give up. Here you go, fine, take them. Take them. That's it. I don't need them. Take them. They will give up those electrons easily, just not as easily as the alkali metals. So alkaline earth metals are reactive, very reactive, highly reactive, just not as much as alkali metals. So here you find the alkaline earth metals, group 2, 2 valence electrons all the way down. So again, they're highly reactive. Give it up, give away those electrons easily. There's magnesium ribbon burning. Okay, magnesium, highly reactive. We can get it to react relatively easily. It reacts with water, again, to make alkaline or basic solutions. They're usually not found as pure elements in nature, again, because of that highly reactive nature. Let's talk halogens. Halogens are group 17, okay? They're non-metals. You can see there's the list of elements. They have 7 valence electrons, group 17, 7 valence electrons. You don't have to remember that. You can look it up. You can see what the configuration is for each of them. They're going to have a full S and 5 in P. You can see going down, if you look at each of those elements, they have 7 valence electrons. 2, so if I just pull this little pointer right here, 2 are in S and 5 are in P. So 2 plus 5 is 7. Okay, so that's how you read that kind of electron configuration. They're highly reactive. So he's going, all right, fine, take it. Super easy. They're just waiting for electrons to steal, and they just do it so well. So they are highly reactive. They are the most reactive nonmetals. So again, highly reactive. They react with most metals to produce salts. They have a wide range of physical properties again. So fluorine and chlorine are gases. Bromine is a liquid. And then we have iodine and astatine that are solids. If you just remember the first two, gas. Next one, liquid. There's only 2 liquids on the periodic table. Got to remember them. Bromine's one of them. And then we go to solids. So luckily it goes in order: gas to liquid to solid. Now, something that you should maybe have noticed is the alkali metals want to give up 1 electron. They're like, take it, fine. I don't need it, take it. I'm happier without it. And then we have the elements in group 17, the halogens, that are like, give me an electron. I want one. Where's one? I want it. Give it to me. Give it to me. Give it to me. They're all ready to take it. So alkali metals and halogens are perfect partners. They love it. Alkali metals want to give one away. Halogens want to take one. So there's a lot of compounds that will form between alkali metals and halogens because they are perfect partners. Now, noble gases. Noble gases is group 18. They're very stable. They have 8 valence electrons. Remember, the exception being helium, because helium has 1 energy level and only 2 electrons fit in energy level number 1. So helium has a completely full energy level, so it is still stable. So remember, 8 valence electrons is stable, or 2 total electrons, okay? So again, 8 valence electrons makes it stable, and there's a couple of 2 different visual ways that you can see the difference between those noble gases. They have very low reactivity. They already have 8 valence electrons. They're like, I'm good. I'm fine. I'm totally good. No, thank you. I'm good. Okay, noble gases on the periodic table, group 18. They're obviously all gases. Shocking, right? The name. So this whole group is all gases. But where else are gases? We have hydrogen. And then we have a little like 7 kind of flipped. So we have nitrogen, oxygen, fluorine, and chlorine. Right here, this little cluster. Those are also gases. So gas, gases, and then nitrogen, oxygen, fluorine, and chlorine are gases. Where do we have liquids on the periodic table? 2 right here. Here's 1, mercury. Here's 1, bromine. That's it. Everything else is a solid. So gas, 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 group of gases, and then liquid, liquid. The rest are solids. So noble gases, again, very low reactivity. They already have 8 valence electrons, except for helium, 2 total. Helium, we use it to fill blimps. It's got low density. It's not flammable. It's not so reactive. Neon has a lot of uses. The lighting is that reddish orange color. We use it in TV sets and lasers, also to freeze corpses. Who knew? There you go. Hydrogen. Hydrogen is the most common element in the universe. 3 out of 4 atoms in the entire universe is hydrogen. That's common. It's 1 proton, 1 electron, sometimes has a neutron, sometimes doesn't. So it's in a total class by itself. So hydrogen, again, total class by itself. It's in technically visually on the periodic table. It is in group 1. But it can react like a metal, it can react like a non-metal, it can kind of do its own thing. Hydrogen can kind of just do what it needs to, okay? But it does react and form a lot of different compounds. So hydrogen can react with many elements. It's flammable. It reacts with oxygen to form water. It's a component of organic compounds. Again, most common element in the entire universe. But which element is in a class all by itself? Hydrogen, right? Which group of elements has 2 valence electrons? Right, the alkaline earth metals, the second most reactive group of metals. Which group of elements contains the most reactive metals? That's group 1, the alkaline metals, right? These ones do not exist as pure elements in nature. Alkaline earth metals barely do. Which group of elements contains the most reactive nonmetals? That's halogens. Remember, halogens and alkali metals, perfect partners. Which group of elements contains the least reactive elements? These ones are stable. I don't want to do anything. Noble gases. Just leave me alone. I'm good. I'm stable. I'm good. Don't need your electron. I'm good. Don't take my electron. Just leave it. We're good.